Hello everyone, welcome to this video. In this video, let us see this question and let's try to answer the question. So the question here is, how do we know whether a given subset of this group that is a subgroup? So in the last video, we know what is a subgroup of a given group. We have also seen various examples of subgroup as well as group. Now, if you are given z as the set of integers and you take say 1 2 3 4 as the set, now can you call this to be a subgroup of the given group because this is a subset of the set of integers, or what are the conditions? So the answer is what we have to do, we have to, in order to check this as a subgroup, what we need to check, we need to check that the group axioms, they all should exist for the given subset under the operation of the group from which the subset has been taken, right? So, and what are the group axioms? They are closure, associativity, existence of identity, and existence of inverse. If all these four conditions are satisfied for the given subset and the operation that we consider is the group operation, then we say that the given subset is the subgroup for the given group. So this person here has this doubt that, but won't it be time consuming, because for every time if we go on checking the axioms, and it would be lengthy process because we have to check it for each of the element which is a member of the given group. So this fellow says yes, it is obviously time consuming. So this fellow here asks that what should I do then in order to save my time? Is there any alternative method? So this fellow here tell you that we have subgroup tests as well, which may help us in order to determine whether the given subset that is a subgroup or not. So to understand this thing, let's move ahead and see a one-step subgroup test. So this test would give you just one condition where if you check that condition, you'll say that yes, the given subset is a subgroup. So what is that particular condition? Suppose G is the given group and we take H as a non-empty subset of G, right? It should at least contain one element. Why? Because we at least require the identity, right? We cannot take it to be empty. If it is empty, it is definitely not a subgroup, right? So if we take the operation of multiplication, group operation as the multiplication, so the condition is that A, B inverse should be there in the given subset whenever you take A from the given subset and B from the given subset. And if you take the group operation as the operation of addition, in that case, whenever A is there in H and B is there in H, then A minus B should also be there in the given subset. If that is so, you will say definitely, and you are sure, you will be sure that this subset H would form a subgroup of the group G, right? So this is one thing. So let's prove this condition. How this is true, you'll be more convinced by looking at the proof of this thing. So for the proof here, we assume that G is the group that is given to us and H be that non-empty subset of the group G. Now in this case, we assume that this condition holds, that AB inverse belongs to H wherever we have both A and B taken from H. With this condition, we now have to prove that the given subset H that is a subgroup of the group G, right? So here we wanted, in order to prove this thing that H is a subset of G, we need to prove the group axiom. So we need to prove the closure property, the associativity property, the existence of identity, and the existence of inverses, right? So let's prove them one by one using this given assumption. So in the first case, we are saying that for the operation of this subset S H, this operation is same as that of the group G, and G is a group, so that means that operation, say, whatever we take, say multiplication or addition, that is associative, right? Whichever operation we take, that would be associated because it is the same as that of G, and G is a group. So therefore we have associativity for this. This is same as this, so therefore associativity would also hold for this. So associativity is done in this case. Next, we wanted to prove that identity exists in the subset H. right? So to show that identity exists and belong to this H, we consider, because we have considered H to be non-empty, so we can choose some element X from it. So we are choosing X from it, and we are saying that if A, B are X and B is also X, then according to this assumption, we have assumed that whenever we take both A and B from H, now because they are both equal to X and both are taken from the subset H, right? In that case, AB inverse would also belong to H. So that means X inverse would belong to H. And what is X inverse? That is equal to the identity operator. So that means we have the identity present in our subset. So we are done with this second condition also. Now let's see about the inverses. So we here, to show that inverse exists, we take some element X from H, and we will show that X inverse would also be present in H. For that, what we do, we select A as the identity, because in the previously we have proved that E is a portion of this H, right? So because E is present in H, so therefore we may select A as equal to E and B as equal to X, right? And because both of them are members of H, so that means AB inverse is also a member of H. So that means E into X inverse is also a member of H according to the condition, because A is E and B is X, right? And what is E into X inverse? That is X inverse. So that means X inverse also belongs to H. So that means our fourth property also hold. Now the last thing that is required is the closure property. So here we wanted to prove that H is closed under the operation of whatever operation it have. So that means we are proving the closure property. So in this case, we are taking the operation of multiplication. So that means if we take both X and Y from H, then their product XY also belong to H, right? We wanted to prove this thing. For that, we know if Y is present in H, then Y inverse is also present in H from the previous part. So that means we can choose A as equal to X and B as equal to Y inverse. We can choose that because both of them are member of H. If both of them are member of H, so that means by our assumption AB inverse is a member of H, because A is X and B is Y inverse. So X, Y inverse would be there in H. And what is the inverse? Y inverse, that is equal to Y only. So we have X into Y member of H, and this is what we wanted to show here. So that means the fourth property also holds in this case, because all the four property hold in this case. So therefore the given subset H is a subgroup of the given group G. So I hope you understood the proof of this one-step subgroup test. In the next video, we'll be looking at the examples and more tests regarding subgroups. Well, that is it for this video. Thank you for watching.